Thanks, Henny, and good morning, everyone. And thanks for the fantastic turnout. And it's great to see lots of new names and lots of people, obviously, active in the gold business. So I'm going to briefly introduce Neil Phillips, and equally Alex Kistas. Neil has been the driver of this 5 presentation series with Alex. And so I would also just like to, while we sort of get into it, compliment and say well done to Alex Kistas, who was last year, I think, awarded the Draper Memorial by the GSSA, Geological Society of South Africa, which is the top award to our geoscientists. And so well done, Alex. But we're going to hear more about that from Neil. Just by way of introduction, Neil Phillips graduated in geoscience from the University of Melbourne, completed his BSc honours there, and then did a PhD at Monash University in 1978. He also has an advanced management program that he did at Harvard Business School. He co-founded the Archean Gold Group at the University of Western Australia in 1980 with David Groves, as they developed the geological principles used in gold exploration then, and for that matter, still today. He was at the University of the Witwatersrand from 1984 through to 87, where he led research projects at the top or 40 operating Wits gold mines back then, certainly not 40 of them left today. And then he maintained these projects as Professor of Economic Geology at James Cook University, and then as the Chief of the Division of Exploration and Mining at CSIRO. He has an honorary professorial appointment at Stellenbosch University and at University of Melbourne and Monash University, which has enabled ongoing research, collaborations, and teaching of gold geology, and allowing him to continue his interest and study in granites. In 1995, he co-founded the Geology of Gold course and still contributes to this annually. Neil was editor of Applied Earth Science, the Applied Earth Science Journal, and the Aussie Institute of Mining and Metallurgy, and did a great job putting together the quite recent Australian ore deposits monograph. He regularly publishes in scientific journals and has written and edited several books. Beyond Gold Research with Julian Verncombe, and a keen interest in the Stellenbosch and Barberton Gold team. He has ongoing research and collaboration with John Clemens and Alex Kistas at Stellenbosch University. So with that, over to you, Neil, and you can set the scene for the next five presentations.
Okay, thank you very much, John. Let me just expand that. Yeah, John, thank you very much for that introduction. And Henny and John and your team, look, thank you very much for the effort you've put in. I've suddenly realised how much work you put in between the Thursdays to make this whole series happen. And obviously it's being appreciated by a lot of people. I've got 2 roles tonight. One is to talk briefly about the series that'll take place in 5 Thursdays during March. And the other one is to talk about Alteration, which will be number 1. The series really comes out of a number of us being excited about the work coming out of Stellenbosch and Barberton Greenstone Belt on the gold deposits there. It's world-class research and outcomes, and I think it's worth listening to and hearing. It started to be published in some international journals, and next week you'll hear more about that, and the week after. Just going through the list, I'm talking about Alteration today. Caitlin Jones has just finished her MSc at Stellenbosch and will talk on her Barberton work next week. The following week, Alex Kistas, who is head of department there and has really head up and led that Barberton research for many years, will give a broader picture on the research. Julian Verncombe's known to a large number of people in Southern Africa, headed up the MSc course in Western Australia, where he had access to and supervised students from a large number of mining operations and exploration. So he's got a really good feel for how does one get good academic work across to on-the-ground mines and exploration, because it's very hard to make that transfer. effectively in many cases. So he'll talk about that. And I'll finish up by saying, well, what have we really got out of the first 4 weeks? And by looking at Archean greenstone gold, and does that help us at all to look at the Witwatersrand gold a little bit differently? I have a rule that 15 words per slide, and I'm not going to break it tonight. This is just put here so that the introduction for the series is captured for those who look at the YouTube after. Shifting then to alteration and greenstone gold. What I want to do is a little bit we call principles and foundations, and that really paves the way a bit for the next 4 weeks, and then go into 4 little areas that I think overlap with what the other speakers are going to say, and all of us have worked together to make a fairly coherent group here of structure, alteration, fluids, mineralisation, and tying them together. And the important part there is the tying them together, because they don't just happen in isolation in nature. I guess that's what it's really about there. What you're looking at is a quartz vein, the white up the middle, and it's got gold in it. And if you go out and look for that, that's okay. Lots and lots of people have been successful. The concept with alteration is that bleached area around there is an alteration halo around the quartz vein, and it's a bigger target. So in very simple terms, the alteration is offering practical help in a bigger target than just plain high-grade gold mineralisation. There's another benefit of the alteration, and that is from the scientific point of view. If we're looking at the quartz vein, there is a limited amount of information you can get out of a piece of quartz. Maybe fluid inclusions, maybe some other things, but you get a huge amount of information, scientific information, out of that alteration zone that will help explain how the alteration zone formed, and therefore will help you on how the gold mineralisation formed. So that's why we're interested in the alteration. What I'll go through is very quickly what I've just called a layman's equation, just what alteration is all about. 2 slides just on Kalgoorlie, because that's where I'm drawing some examples from. I did that deliberately because there's a lot of similarities, and I didn't want to draw my examples from Barberton, and of course I don't know it as well as the following speakers. But you'll see the similarities, and I think things will flow from week to week around some of those. The topics I talk about, we'll delve into textures and strain, concepts there, so obviously the link to structure. Mineral assemblages, a really important way to step forward and up and get more information out of alteration. Geological properties, which I'm really only just mentioning, but is key to a lot of weeks number 2, 3, and 4. I'll talk a bit more length at whole rock geochemistry, how we can use it. And I'm going to just finish up very quickly by saying how similar weathering is to some of the things in alteration and how it might differ. And the triangle, the Barberton triangle, and what it's got to do with bronzewing. But you'll hear a much better explanation of that next week. So the layman's equation of alteration. It's a chemical reaction. It's a chemical reaction before normal rock interacting with a fluid. Those two react, and so you get a different rock, an altered rock, that's our alteration, and you get a different fluid. So that's the thing we're looking at, the alteration. It's undergone this process of things on the left, the reactants combining to give things on the right. And here's the practical side, why it's important, because that fluid might contain gold or other metals at the start on the left. As it goes through that chemical reaction, concentration of gold might change. Now, it could go higher or it could go lower. And if it goes lower so that it precipitates all the gold, then we're well on our way to forming a gold deposit. And exactly the same principles can apply to any other metals you want to dissolve in fluids and potentially form an ore body. So that's the practical side of why we might be interested in studying alteration. So the young geologist yells out, "I think I've found some alteration." And the senior managers, who are very supportive, says, "Well done, this might help us and lead us to a discovery." very encouraging in their words. And my mate in Townsville says, we'll move. Now, what he means by that is we might be standing on a little bit of alteration, correctly identified. But his comment there says, move left, move right, go forward, go back, go up, go down. Because it's not just I'm standing on a bit of alteration, but how big is it? How does it change as you go left or right? Where might it be getting more intense? What's the whole dimensions of it? And does it relate to other rock types there, or do we have a very big ore body or something we should just walk away from? I think the other thing that Julian Verncombe and I have been sort of talking about for years is nobody ever reports that they used alteration to find an ore deposit. In all the discovery histories, you hardly see it mentioned. And yet I'll bet almost every single person who's looked for gold for the last 200 years around the world has paid attention to pyrite. And it might be pyrrhotite or something else, but sulfides. Now, they're not doing that because they're trying to mine commercial pyrite. It's got no value. They're doing it because it's an alteration product of an inferred gold formation event. So we're actually using alteration the whole time in that way. We're just not describing it or thinking it that way. So back onto our quartz vein, the white up the middle. It's got a very small selvage of chlorite, the dark green. It's got that bleach material around it that is actually coarse-grained basalt or dolerite, and then it's got less altered material out to the top right, and particularly the darker green to the bottom left. And we're going to draw a few examples from Kalgoorlie. So quickly on the geology, there's the map of Australia. There's the Archean Yilgarn Craton in the southern half of Western Australia. You're looking at about 80 million ounces, so the largest Archean greenstone gold deposit. Golden Mile dolerite is the main host rock, but not the only one. We're only looking at gold, so it's like Barberton. We're not looking at a multi-commodity mines at all. You're not looking at lots of copper, lead, zinc, and it's been operating for well over 100 years. Some of the features of Kalgoorlie, and I've been a bit selective here to draw things that are useful in the 5-week period. There's many host lithologies, but it's predominantly mafic rocks, some sedimentary. Again, coming out in the 4th week, Julian Verncombe will talk about this idea of structural complexity. If you've got a single thin quartz vein that goes right around the world, you won't get a major gold mine that lasts for many, many years. You need different types of structures and or different orientations of structures and repetition. And Kalgoorlie's got that. And we've got water, CO2, sulfur fluids, which many will be familiar with, and I won't talk more about that, green schist facies. And the minerals that are important are carbonates, sulfides, muscovite, and chlorite. So let's swing around to the first of these little topics of texture and strain. And by texture, what I'm talking about is I pick up rock number A, and I look and I say, that's got cross bedding. And I can work out from that texture that it's formed in water of a certain depth and flowing and doing these sort of things. So I can work something out from the texture. And I pick up rock B, and it's got feldspar laths sitting in a sea of clinopyroxene, and I say to myself, I recognise that texture, and it's an igneous texture, and so forth. If those sit in the middle of a high strain zone, we'll call it a shear zone or fault, whatever you want, then the textures are destroyed. So you can look at the rock and it becomes a quartz-rich schist, or it might become a chlorite schist, but we can't look back because the textures are destroyed. So that's the whole point, the high strain and the textures. This example is back to the Golden Mile dolerite. On the left, dark green dolerite, coarse grain basalt, if you like. There's a cream buff colour, and that's altered, but low strain. I can see the textures in it, and we'll see that in close up in a moment. And right up the middle, the mineralisation has got lots of wispy quartz veins, and you can't see any textures there. So that's a high strain zone, textures destroyed. Let's look at it further across that boundary. I think this is a really nice example here. Bottom left is chlorite, dark green, and you can see the textures there of the feldspar laths, the pyroxene, that's sort of sitting all around it. And there's the titanomagnetite clusters there. Now, when you swing across to the right, we can still see the feldspar laths, but they're not feldspar anymore. We can still see the interstitial or pyroxenes around those feldspars, but it's not pyroxenes, and we can still see the titanomagnetite. The feldspar laths have gone to carbonate and muscovite. A lot of the chlorite, which is after clinopyroxene, is now carbonate, and that's why it's bleached and white colour. And the titanomagnetites have gone to rutile and pyrite. And this is a classic example of the link between strain and alteration. I think everybody would agree we're looking at an ammonite. And those who know their paleontology really well might look at it and look at sutures and so forth and tell me exactly where in the Jurassic it came from. It's really well preserved. And it's well preserved because it's not caught up in a shear zone or anything like that. It's undeformed, low strain. But the other interesting thing about that is that ammonite is predominantly pyrite. Now, it didn't float on the surface of the ocean as the only pyrite ammonite around, and it didn't land on the bottom when it died as a pyrite ammonite. It happened after burial, or happened sometime later after death. And as such, the textures are preserved beautifully, and we can recognise it, but there's been complete alteration, and it's basically a new mineral altogether. And so that's the contrast there between high strain, low strain, and alteration. Topic 2, talking about mineral assemblages, and this is a really powerful area that some people do exceptionally well. I could talk to you about alteration and say that's propylitic alteration. And I would say at least half the people on this meeting wouldn't understand what I'm talking about. And in fact, I don't either. So I've failed to communicate much at all. I could say, perhaps in a case of a porphyry copper deposit, we're looking at potassic alteration. Now, I've conveyed that it's potassium that's been added, but I haven't really told you if it's K feldspar, muscovite, biotite, or something else. So again, I have failed to communicate as much information as I could have. Or I could have said that's chloride alteration. And that's quite specific. It's telling you what the dark green mineral is. But we can do better. I can convey much better information saying we've got a coexisting mineral assemblage here of chloride, albite, muscovite, quartz, magnetite, hematite, pyrite, siderite, and anchorite. And in actual fact, that's what you saw in some of those earlier ones. Now, from that, true, it is a chloride alteration, but you've got much more information here. You can work out from that the pressure, the temperature, oxygen, sulfur, and CO2. And so you've actually learned quite a lot about how that alteration, well, that particular sample formed, and put that together with a few other samples and through inclusion work perhaps and other things. You're starting to get a real handle on the physiochemical conditions under which the alteration formed by looking carefully at that assemblage, actually treating it as a metamorphic assemblage and saying, tell me what's there, and I will work out some of the conditions under which it formed. Next topic, rheology properties. And I'm only going to touch on this very briefly because I think you'll hear some neat stuff the next 3 weeks. The addition of potassium, which I used as an example just a moment ago, could form micas or it could form K feldspar. If it forms micas and you get a mica schist, that's clearly going to deform in a certain way. If you form K feldspar plus, say, plus quartz, it's not going to be a mica schist and it's going to deform in a very, very different way. And I think that's the point that Caitlin and Alex are going to make, that the alteration, and depends what minerals you're dealing with, the alteration then determines a whole lot of things about ongoing deformation. I've chosen extreme there between micas and K feldspar, but there's a more subtle, really interesting differences. What we're looking at there is back to the same example. Over on the left, we're looking at low strain, doleritic texture, dark green. On the far right, we're looking at quartz veins. It's all a bit wispy and vague. That's part of the story. But we're looking at those vertical little channelways or slivers that are made up of muscovite and pyrite. You can't see any textures in there. That's just really like a schist. And so you're looking at high strain with muscovite along the edges of the quartz vein, with gold, with pyrite. And then as you go out, the strain gets much lower and you can start recognizing textures. Those black dots, I think, are tourmaline. This is published, and it's a pretty nice example because the top two are looking at strain. The bottom two are looking at alteration. And top left, the green is the chlorite and it's low strain. We can see textures. And the little orange things are low strain and we can see textures. On the right, the red is high strain. You won't see any textures in there. It's all wispy quartz veins. And those slivers of muscovite, pyrite, and a bit of gold. Bottom left, we're looking at a chlorite zone out to the right, the dark green. We're looking at a carbonate zone bleached. And in red on the bottom right, we're looking at a pyrite zone with muscovite, carbonates, pyrite, quartz, and high gold. And so that's really the target. And the reason this is still left in this drive 100 years later is because there's nothing wrong with the gold grade. It's just a little bit too narrow to be economic. Whole lot geochemistry as applied to alteration is a big topic. And for economic geologists, there's a huge amount we can learn from igneous geochemistry particularly. So going back to normal rock plus fluid gives our alteration. Let's examine the normal rock just for a moment. The normal rock, and you can think of sandstone shales or basalts or komatiites or whatever, is made up of major minerals. The major mineral forming elements, and those major elements are the silica, titanium, aluminium, iron, manganese, magnesium, calcium, sodium, potassium. And they're there over and over again because they make up most minerals in most of the crust, in most rocks we deal with. It can be made up of those, plus water, plus CO2, plus sulfur. I'm not going to talk about manganese anymore. It's actually not important in these systems, but we're going to look at the rest of the major elements. Now, if we're dealing with a basalt, and I'm simplifying this a little bit, has virtually all of those major elements except potassium as essential in essential amounts, forming minerals. Shales have a lot of those elements. It does have potassium, of course, in the form of micas, but it doesn't have calcium and sodium as essential elements. And as you go down that list, it's a little bit more simple in terms of essential major elements. By the time you get to a quartz-rich sandstone, just think what we've got. We've got quartz, we've got silica. And if I look at that sandstone at 50 degrees, it will be quartz. And if I look at that quartz-rich sandstone at 400 degrees, it's quartz. And at 700 degrees, it's quartz. So from a metamorphic point of view of trying to work something out, a quartz-rich sandstone is as good as useless. It's very, very difficult. So I can't look at that quartz-rich sandstone and say, oh, I can tell you that that's never been metamorphosed or it's been to 700. Go to the basalts and the shales, and they're very powerful because large number of elements will give you a large number of minerals, and you combine those together and say, right, I know exactly where we are. And of course, that then goes to, you look at basalts and say, well, at lowish grade, those could be zeolites or prehnite pumpelliite, chlorite and actinolite, or amphiboles, or pyroxenes, or eclogites, or blue schists, a wide range. And of course, our metamorphic facies derive their name from the basaltic assemblages because they're so useful. And the shales are much the same, where we can get our muscovite, biotite, K-feldspar, andalusite, sillimanite, kyanite, cordierite, garnet, and so it goes on. Lots of minerals, really helpful working things out. So we're being a bit selective in what we choose and try to look for. Now, still just on the principles before we get to look at some geochemistry, what dictates the elements that move in an aqueous fluid? Well, there's charge on the element and there's ionic size, and those both play a role in how conveniently and tightly different elements fit into different minerals. And the two are related in that, think of a cation there, think of a charge on the nucleus, and if that's +1, the attraction on the electrons is quite small. If it's +5, the attraction on the electrons, which are negatively charged, is quite strong, and the electrons are pulled in, so it's smaller. So as valence goes up from +1, 2, 3, 4, 5, the ionic size goes down. And so things that are big and low charge will float around easily, and things that are high charge and small will generally be tightly bound. Now, I know there's exceptions to that, but it's a pretty good starting point. I'm going to look at 5 element groups, not evenly, but just to cover the names. We talk about large iron lithophile elements. They're column 1, +1, a little bit of +2 as well. You take something like potassium, K, +1, little attraction on the electrons, so it's large, doesn't fit in very well, and so it goes in and out of all sorts of solutions, whether it's weathering, porphyry coppers, greenstone gold, or whatever. It's always going to be mobile. And that's characteristic of that group. Now, we don't know much about rubidium, but we can certainly work out from this table and say, I would expect rubidium is going to follow potassium. And in fact, of course it does. The second group, first transition series metals, to a chemist, they're all pretty much the same, and they are the same. They've got a lot of similarities and they get this common name as well. But of course, as economic geologists, we know they're very, very different, and we get iron ore formed in some places by some processes, manganese somewhere else, and cobalt, nickel would be somewhere else yet again, and our base metals. So what nature's doing there is it's picking on small differences between iron and manganese, or between copper, zinc, nickel, and cobalt. So there's similarities in the group, but there's also important differences. This is an important group we're going to talk about with the alteration geochemistry, counting across +1, +2, +3, +4, +5. So we're looking at +3 to +5, and we can have +6. So these are going to be small, tightly bound, and are not going to go in and out of aqueous fluids easily at all. We would expect these not to be involved in being added or subtracted in alteration. And the rare earths, again, counting across +1, +2, +3 for lanthanum. So these are all +3, the rare earths shown in blue there. 1 or 2 of them have different other valences as well, but we'll treat them as +3, and we'll say, here is a very coherent group that to a chemist is pretty similar all the way across. And that's true. And yet the igneous petrologist will look at those, and they'll look at very small differences between those on the left, the light rare earths, and those on the right, the heavy rare earths, and say, because of the slightly different behaviour between the heavies and the lights, I can now work out something about garnet in my melting region, or somewhere else about plagioclase. So they're looking at subtle differences among a relatively homogeneous group. But again, high charge, and we would expect those not to move in and out in an alteration event. I add these for completeness, another group we should be interested in: water, CO2, sulfur in the auriferous fluid, potassium, rubidium, we've talked about. Silica is going to move around at will by its own set of rules. And of course, it gets expressed as quartz veins. And this group of very interesting elements, arsenic, gold, silver, boron, antimony, selenium, tellurium, mercury, moly, and bismuth. And you'll recognise those, anyone who's explored for gold will recognise that and say, well, they often go together. And if I found a fair bit of arsenic or fair bit of mercury, I'd probably pay attention and say, I might be in gold-bearing country. So they're all going to move in and out very easily in these gold-bearing fluids. Okay, I'm going to switch back to the major elements because the major elements are what dictates the minerals you see mostly. And I'm going to look at the bottom left, the dark green, less altered, and the top right, more altered. I should be a little bit careful here. The bottom left is less altered, but technically it's not completely unaltered. Now, we've done an analysis of the dark green and the cream coloured. We've got our chemical analyses. We've arranged those there in silica, titanium, aluminium, iron, manganese, and so forth. There is a very good reason why those things are arranged in that order, and the igneous petrologists are going to sort of roll their eyes when I say this, but papers still come in economic geology where people say, oh, I've put those in alphabetical order to help you, or I've put them in the order that I got from the technician who got it from the computer, who got it from the analysing machine. And I think if a paper is submitted like that, it's just about, it's going to very struggle to get through because the person clearly doesn't understand why the major elements are arranged in this order. There's a good scientific reason, and it's been done globally for 100 years. So unless there's a good reason, don't change it. It's part of good communication. I could show that to igneous petrologists and they'd look and be very familiar with the order. Let's look at the changes there that have taken place between sort of the middle column and the right-hand side column. Not much in silica. Titanium, aluminium, down a little bit, iron, the same, calcium, the same. Sodium fraction, big jump in potassium as we go from green to that cream colour. No surprise because we've got muscovite. Big jump in CO2, absolutely no surprise because we've gone from chlorite, dark green, to carbonates, and I'm talking about anchorite in particular, maybe siderite, maybe calcite. And big jump in sulfur because we've gone from titanomagnetites to pyrite. And if you look at just a selection down below, you could have 50 elements here, but the rubidium's gone up a lot because it follows potassium, yttrium, zirconium, hafnium, with those high field strength elements all down just a little bit. Now, we need to understand what we sampled to get those two, because this will explain why some of those are down a little bit when perhaps I was trying to indicate that they don't move. That little red line is a idealized sampling bit of core where we've taken bits of pieces to analyze less and more altered. And you can see from that, firstly, we've tried to avoid the large quartz veins because they're just going to give us 98% SiO2. But however much we try in a photo like that, you're not going to avoid the really small little wispy bits of quartz veinlets and so forth. So you're going to get some contamination. So rather than trying to completely avoid that, we're going to acknowledge it. This is just one way of handling those two sets of numbers. The final column, 98, means that second column is 98% of the first column. 82%, 82%, and so forth. A huge increase in potassium and CO2 and sulfur, huge increase in rubidium and yttrium and zirconium, 82. Now the 82 is a little bit of a fudge because I rounded some numbers. So it's a little more perfect than it should be. But what we're seeing there is a whole lot of elements have gone down by about 18%. And they're the ones I said shouldn't move. And the answer to that is just here. What's happened is we've picked up in our sampling a whole lot of wispy little bit of quartz, which is SiO2, and that's had the effect of diluting everything else. So we might have added 10% quartz, for example, and that keeps silica up and it pushes the immobile things down. So the titaniums and aluminiums haven't moved, they've been diluted. A summary of our major elements there. Silica will do its own thing. Sodium and potassium generally move a fair bit. They're +1s. The +2s can vary a bit. And the example here, they're not moving much. Other places they will move a lot. Titanium and aluminium are our best option as starting, likely to be immobile because they're +4 and +3. There's lots of different ways to represent alteration once we've got the geochemistry. I've just showed a simple ratio plot there with the 82% and so forth. We could do XY plots and they might be a bit more informative. I'll talk about a Kerridge diagram in just a moment, just a name I made up for this. But we can do Gresson's analysis, isocon plots and all those type of things, spidergrams and so forth. Now, with respect to all of those, they're all just telling us something about ratios between perhaps a starting point and a finishing point. Now, there's no brownie points for putting in a Gresson's analysis or a spidergram or whatever. The real value, be it in a paper or thesis, is to put the intellectual input of how it was collected and what we're actually designed geochemistry for. And at the other end, now I've done the diagram or diagrams, this is how I interpret it, the intellectual interpretation. So the diagram itself is just a ratio. It's the brain power that really counts. I put this in, it's very old. I put it in for several reasons. The late Rob Kerridge introduced this sort of thinking to greenstone gold to a large extent in the early 80s. He spoke at Gold 82 and he used this type of diagram at the Barberton Centenary in 1983. I hope that was the right year, I think it was. What he's done there is two different rocks, and it could be, but it's not, it could be the dark green and the bleach material. The dark green is the baseline 1 going all the way across, and the columns or bars are deviations from that as you alter from less altered to more altered. So you see rubidium, potassium, gold, sulfur, and CO2 go up, no surprise, and everything else hangs around close to 0. In other words, the rest haven't moved much. And this is the same 5 elements that have gone up a lot, but there's a bit more scatter, and you can see most of them, particularly the ones we said shouldn't move, have all gone down. And again, I'd look at this straight away and say, I think you're looking at 5 or 10% dilution by quartz. It's not a case of all of those have actually been mobile and moved in and out. They've been diluted. So we can sort of wind back and say, what have we learned from that? Well, basalts and shales are going to be very good for alteration studies generally because they've got a large number of major elements and therefore they have the potential to form a large number of minerals that will be able to tightly constrain conditions during which whatever it is happens, be it alteration, be it metamorphism. A pure limestone is actually not all that helpful. A dirty limestone is much better. And an ultramafic, if it's a pure dunite, you're going to be struggling to get much out of it. If it's got a little more sort of towards the mafic end, it's obviously going to be better. And with our quartz sandstone, I said already that it's very difficult to do much in these type of studies with pure silica. I just put this in, not to go through the list, but to really have it there so people can come back to it later on. It's a list of immobile elements that work in some or a lot of gold-only systems. Now, there's 2 reasons why it's worth paying attention to this. And when I say paying attention, do not take it for gospel. At your gold mine, 1 or 2 of these may not work. And you might find other elements like chrome perhaps does work. So don't hesitate to use what you find. But this has a practical basis in that it's based on a lot of studies in different greenstone belts around the world, Canada, Southern Africa, Australia, Brazil. That's the practical side. It's got a theoretical side too. We're going right back to the start saying these are high valence, low size, low radius, and therefore they should be tightly bound. So they should work. And in fact, science is on our side there. So it's got practical and theoretical basis. A quick word on weathering. Weathering is physical and weathering is chemical. I'm talking about the chemical side. A lot of weathering is very similar to what I've been talking about with the alteration. And of course, in weathering profiles, potassium, for example, moves out at the drop of a hat. So a lot of things are removed and you end up going from a complex rock maybe to a clay zone. And generally we think of weathering taking place at 25 degrees C, but of course, as you go deeper, you still may be having weathering with surface waters going down and temperature could be above that. So it's a bit of a grey area between what sort of deeper weathering. Alteration, I would generally be talking about as 200, 300, 400 degrees and up that way. But there's clearly a grey area where it's a little bit harder. And keep in mind, weathering does go down to hundreds of metres. It does go down to a kilometre, and rarely it goes down to 2 kilometres where we've got special rock types and we've got special topography. Finally, let me finish on the tantalising triangle, and you'll hear the proper story next week on this. But Bronzewing gold deposit is here. It's about 5 hours drive north of Kalgoorlie in the northeast Yilgarn Craton. And I just put this diagram in because it's now 35 years old, I think. Oh, the diagram, yeah, the original diagram is. Top right, we're looking at Sheba Fairview there in that triangular area or cusp of Barberton in a diagram drawn by Sarah Houston when she did her PhD at Barbrook in Barberton, Greenstone Belt, and David Groves, and they published this. And we took a look at this and said, well, what about looking at the left, what about these cusps in Greenstone Belt where you're sitting next to granite, and maybe we should explore there. And that was one of the bits of thinking that helped to focus in on Bronzewing in 1992. Now, I think you probably find a very different explanation to how or why that forms and a much better answer. But it also highlights something. You see a pattern and you don't wait around 35 years until the scientists get it right. You act on it, and then you're prepared to either be wrong or to say, well, I got there looking for pattern recognition and I didn't quite have the science right. And as the science gets better, you might have more and more confidence. So I'm going to finish with this one here, and this is Bronzewing at early stage. We're just going to look at the weathering. And keep in mind, a lot of the chemistry here is the similar chemistry to alteration, but taking place at low temperatures. The dark green in the bottom there is unweathered metabasalt. Above that are lots and lots of different colours of oranges, purples, chocolates, browns, and that really is partially weathered where the iron is in a higher oxidation state and you're getting all the colours. Then when you go up to the kaolinite rich part there, what's happened there is that's basalt. It's extremely weathered basalt where everything's been removed. So all your major elements have been removed except for aluminium, probably titanium, but aluminium and silica, and they end up making just kaolinite. So you've turned a rock from dark green, you've stripped out the iron and all those other major elements to leave behind just aluminium and silica, and the rock's gone white. So that's weathering, but it's got a lot of similarities to our alteration, which I'd really be talking about at higher temperature. Now I'm going to finish there. As far as supporting documents, particularly for the recording of this, the references, these are the papers from which those diagrams were taken and the stories were sort of evolved. And on those 2 pages, and hopefully Formation of Gold Deposits book will come out from Springer in the first half of this year. So more news on that later. I'll leave it there, say thank you, and certainly welcome questions.
Thanks, Neil. Well done. And as you said, you've opened it to the floor. So Henny and I'll help him. We'll manage the question and answer session, either through raising hands. People presumably know how to use Zoom, or first come, first serve. So over to the audience. Okay, there's a question. Can you see the chat group, Neil, from Matthew Huber?
I can see Matthew, but he hasn't got his mic on.
No, no, can you see the chat? He's put it in the chat box.
Oh, sorry.
Yeah.
Take it back.
This is, do you have a way of accurately quantifying the silica contamination in samples?
Look, generally speaking, it's not a case of measuring how much in the way of quartz veins you've got in your sample. You do take a look and say, I've got not much or quite a lot. Generally, it's answering your question backwards by saying 10 of my immobile elements have all gone down by 7%. Therefore, my best interpretation of that is not that the immobile elements have moved, but that I've had whatever it is, 8 or 9% silica added. But keep in mind, it's not just silica, and perhaps I should have mentioned that as well. It's obviously CO2 as well. So CO2 and quartz veins are pressing everything else, diluting.
Okay, Matthew, does that answer? You got any points you want to clarify?
Neil, is there a particular reason that you leave granite out of your list of basic rocks? John Blaine wants to know.
I didn't try and cover all rocks, but when you think of granite, granite's actually really just quartz and feldspar with a little bit extra. Sorry, I've offended John Clemens when I said that, but granites are going to be not nearly as useful as something like basalts or shales that have got a wide range of elements. So what you really want is you want a bit of everything to get a wide range of minerals. When you heat up or alter granites, my experience is you don't get much out of them in a metamorphic sense, and you actually don't get a great deal out. Well, no, that's not quite true. You do get quite a bit out in the sense of alteration, but it's perhaps not as good as the other types. You end up getting things like muscovite, biotite, but you don't get a wide range of carbonates or other things because there's less of the iron, magnesium and calcium. When I talked about 4 of them there, 4 rock types, you could add another 20 or 30 and you could actually work through each one and say that'll be fairly good or that'll be better or that'll be worse. But I just chose really end members, and it's always worth going in and thinking, am I going to get much out of this? The clean quartzite in the Moody's probably won't tell you much. A shale in the fig tree would tell you a whole lot more if it's an alteration study. What? Gordon. So when I went to Gordon Cole. Gordon, width of the alteration zone. Qualitatively, it will be how far fluids can sort of do their influence going out. That's on cracks and permeation and how wide the network of cracks are, but also the reactivity as well. So some rocks are highly reactive, others not much at all. And you often see, if you've got a layered sequence, and perhaps I'm thinking of skarn type deposits and things like that, sometimes one unit is highly altered a long way out, and another unit, you have a look and say, geez, nothing much has happened to that. And that will be a reflection of different rock types being reactive or not reactive. Can this create an opportunity for CO2 storage? From Gary Williams. I think probably the place people are using a little bit of science here would be looking at serpentinites and things like that and trying to perhaps carbonate those on a big scale and ideally send them down a subduction zone. But whether that works or not, I'm not sure. I do know Andy Tompkins and Katie Evans have a research grant looking for that if you do want to follow it up. I have no idea if it's commercial yet or not, but they're just looking at the science and saying, look at these ultramafic rocks, add CO2, get carbonates, right, now sort of flush that away.
You're muted, John.
Thank you. Just talking as a non-gold geologist, Neil, and I presume, as you said at the start, we're looking sort of more typically at these, greenstone belts, basalt-hosted gold deposit shear zones. And I presume the beryllium stuff will be broadly similar. What sort of temperature or pressure depth do these deposits typically form at? Round figure.
The idea these are forming at 300, 350, maybe up to 400. And I think that I'm pretty sure a lot of the Barberton ones would fit into that. You then get to things like consort, where you look at the temperature indicated by the assemblage, and it's garnets, biotites, and those things, and you say, hey, that doesn't fit. And you get other ones like Tropicana and granulite facies. Now, that's where scientists diverge, and we either think those formed at 350 and got metamorphosed later, or, and perhaps David Groves and Rich Goldfarb are the ones who would push this, they say no, they form at 800 or 900 degrees linked to the mantle. So there's two different schools of thought on how the high metamorphic grade ones get there. But my sort of feeling on that is probably all of them form between 300 and 400 degrees.
Okay. Interesting. And
of course, that's again tied in to, that's a little bit lower, or as in above in the crust, where a lot of the fluids are coming off as you turn a green schist facies with 5 or 10% water into a amphibolite facies with 1 or 2%. You've got to lose that water and CO2 and hopefully a bit of sulfur and hopefully a bit of gold. And ideally that would be where your fluid heads up and forms your Sheba Fairview.
Brian Mapingere has got a question for you. Can you read that, Neil?
Yes. Yeah, interesting question on, take a thing like muscovite, can we form it hydrothermally or magmatically hydrothermal? I think there's probably terminology here in that hydrothermal really these days is hydro water-based, thermal hot. And you can get hot fluids in the Earth's crust by several different ways. You can have diagenetic waters in a buried sequence, and we'll skip those. They're sort of the oil field people's domain. You can get fluids released from, let's say, a granite as it crystallizes. You can have fluids given off during metamorphism. And they're obviously important too, because metamorphic belts or metamorphic provinces are huge. And so giving off 5% water is a big deal. So I guess the answer is yes, there's lots of different ways you could form muscovite. It's really a case of having the right elements, potassium, adding it to your aluminium silica, and being in the right temperature range so that you get muscovite rather than you get K feldspar or something at high temperature.
Now tell me, in the sort of day-to-day productive mining, how would this be used as a tool to chase down the optimum mining direction?
I think there's two ways that come to mind straight away. One is you're exploring undercover, or you're exploring in the weather terrain. You've done a bit of drilling and you say, there's some interesting things there. Maybe I should put together the pattern, the story with my 100 drill holes. And you've got a few things to look for. Now you can look for gold grade, but that's sort of one-dimensional, or you can add to that sulfur, and people look for pyrite. Good, that we're happy there. But if you add carbonate as well, and perhaps whatever else is relevant to where you're working, then you're going to get a much better story or more detailed story. And it might help you to say, I understand this alteration. It's got nothing to do with gold. Let's get out of here. Or this looks red hot. This is the sort of thing I see around Kalgoorlie or Sheba Barberton, Sheba Fairview. I can't afford to leave. This is a big system and I should be here. And I might take out more ground and do more excavation. So it'll help that way. Whether it'll help you turn left and go 400 metres, ideally it works like that, but in reality, not always quite that good. And then of course, underground mining, it's often the alteration zone or the alteration that carries a lot of gold. So that's going to be part of what you mark out and say, I'm going to mine that because it's carrying 2 or 3 grams.
Okay, then a couple of questions that's coming now. If you can read it down from Mahmoud, who's online. He's just not. Well, why don't you unmute and pose your question, Mahmoud? You're still muted. If you can just unmute yourself.
So I've made a mistake with the Barberton Centenary, 84. Yes, I accept that, Stephen, and I do remember our trip down the Swartkopje shaft. I learned a lot in those days. It was great.
Carry on, Mahmoud.
Hey, I want to ask Neil about something. How can we differentiate between intrusion-related gold deposit from porphyry gold? Both of them have potassic alteration.
I think to just look at potassic alteration or potassium alteration is not going to help us a great deal by itself. And the reason there is potassium is going to move in almost any system you want. Potassium will find a bit of aluminium and you're going to get either muscovite, biotite or a feldspar. It could happen in a porphyry copper, it could happen in a tin deposit, it could happen in weathering in the reverse, like taking it away. And of course, it can happen in lots of other areas. And you're going to hear next week where it gets added and it changes the rheological properties of the rocks. So they deform differently.
Does that answer your question, Mahmoud?
No, thanks.
Okay, then Julian wants to know where in the RSA is the best alteration that is underexplored.
And we're ready to go staking based on that question.
Just a little bit south and west of Joburg.
Maybe Julian should be telling us.
Yeah. Michael van Staden wants to know. Yeah, sorry, carry on.
John, Neil, could I just ask a question here about the role of carbonate and some of the mines in the Barberton area, and I'm thinking specifically of the Agnes line and also in the Murchison belt. Carbonate plays a huge role, carbonate alteration, calcium carbonate with magnesium at times. But it looks as though maybe quite a bit of the carbonate is a precursor to the main mineralizing event. And the competency of that carbonate has resulted in fracturing, and that's where the gold antimony and veins tend to occur. So I just wonder, there's a lot of speculation. Trevor Pearton has done a lot of work on this kind of thing. What your comment is on these huge influxes of carbonate, and are they good general markers for gold mineralization in the right terrain?
Yeah. So first of all, Richard, lovely to hear from you. Thank you for your question, and it's good to sort of catch up. You're completely right with what you say about Barberton and those carbonates and the fracturing and all that. And there's some really good examples from both Barberton and Murchison. I think that's correct in that just carbonate by itself is not the total answer, and that's why there are large carbonate, call them alteration halos or whatever, and they seem to have nothing to do with gold. And some of the students at University of Western Australia have sort of pointed out maybe different periods of carbonate alteration, some related to gold and some not. The part you say about how it veins and it's a host for gold later on, that really is sort of following Trevor Pearton's work. That's really part of the story coming out next week and the week after, where alter the rock, and in your case, it's change it by adding carbonate, and it's going to behave differently when you deform it. You could alter it to carbonate, you might alter it to a muscovite schist, you might do something else. And each of those is going to behave differently and will be good or bad for subsequent gold. Just one more thing on the carbonate that becomes useful is there's three main cations that make up carbonates in these systems: iron, magnesium, and calcium. Forget the manganese. If we said all of those didn't get added or subtracted, that's what we concluded with our 82%, then the ratio of iron, magnesium, and calcium in the altered rock will be the same as in the starting rock. And what that means is the carbonate type is determined by the starting rock. And so if you alter a ultramafic, you're going to get magnesites and perhaps dolomites. If you alter a iron-rich basalt, you might get siderite and anchorite. A lot of people look at those and say, oh, I've got different carbonates, I must have different fluids. And the answer is no, you've almost certainly got different host rocks. And sometimes it's easy to know what your starting rock is, and other times it's quite tricky. I think a lot of the barberting things, it's quite tricky because you can call something an ultramafic, but we know ultramafics can be quite sort of variable from sort of dunites at one end to sort of komatiites and proxenites and peridotites and so forth. So all of those will have slightly different behaviour in alteration and in deformation. Long answer to a short question.
Yeah, thanks, Neil, for that. Very interesting, and thanks for your talk. Fascinating. Thank you.
No, thanks, Richard.
Neil, Michael van Staden wants to know what happens to the remnant fluence after alteration has occurred, i.e. the right-hand side of the layman's equation. Can that be sampled and measured and to sort of balance it, the equation, to say the lack of means something?
My experience is no. In theory, it's a good idea. The question is, you might go some way further away and say, I think this is it. And then someone else says, oh, no, it's not, that's come from somewhere else. It's really hard to sort of say, I've got the fluid after it departed from forming Sheba Fairview or whatever. So it's hard to actually make that sort of geological or field connection. The other thing too is, go ahead.
No, just statistically, no, we're just looking at that.
Yeah.
No,
So,
thanks for that, John.
Yeah, it's not easy to sort of collect the right samples to come to that conclusion.
And then Rutger Lecoq wants to know, what is the significance of graphite in and adjacent to shear zones within gold deposits?
Yep, I saw that question, and thank you. That's a good one, because in some deposits it's just very, very common, and it's I think there's probably examples where it gets moved around, maybe as hydrocarbons and so forth, but particularly where it's black shale. The great thing about carbon, which is elemental carbon, so naught is the charge, it's a fantastic reductant. And it doesn't matter if you're carrying around zinc or copper or lead or gold. It's just wonderful at turning a plus charge, all of those being plus 1, 2, or 3, to 0 or sulfide, and then you just get precipitation. So it's working as a reductant, it's causing precipitation, and that's probably why there's that relationship in lots of deposits in sort of almost every greenstone belt I can think of. And the chemistry you're looking at there is really no different to the carbon in leach, carbon in pulp type thing, where we want to get gold into solution and then we want to get it out of solution onto carbon so we can sort of manage it better.
I guess you'll cover that in the VITs too, the carbon leaders and all of those fascinating deposits.
I can try. I don't know how much I'll cover.
Any more questions?
Yeah, there's one on Bronzewing.
Okay.
The answer, Noko, is we are looking at competency contrast there. And in the case of that, well, Bronzewing and the Barberton triangle, you're looking at a greenstone belt and a granite. So in simple terms, there's a big geological difference there. And in more specifically, your greenstone belt, of course, can be sediments or basalts or ultramafics, and they're not all going to be exactly the same. So I think if I can park that question and hand that on to Caitlin next week, she's going to give you a much better answer than that, because she's also going to talk about that triangular area that you're alluding to. I think the point I want to make with Bronzewing there is we don't always have to hang about until the science is completely sorted out. A good explorationist will grab an idea and say, I think that makes sense and I want to get out there and use it. I'll prepared to bail out and say, okay, we got it wrong, or run with it. But waiting for 100% proof when the whole world agrees on something is not a good exploration strategy. I want to be sort of first mover or close to, if you can, get out there and take a risk.
Well, I think that's a very good cue for us that you've now mentioned the second of the 5 talks coming up. And just by the comments, you've set the table for a very interesting series to start. And we're looking forward to another record-breaking attendance where we reached 100 today. Thank you very much, Neil, and everybody for attending. And hope to see you, most of, if not all of you, here next week.
Thanks, Henny.
Yeah, thanks, Neil. That was fantastic. And thanks to you, Henny, and thanks to Nolene for all the admin work. It's been a real good turnout, and thanks to all the people that participated and for all the good questions. Got to keep Neil and the rest of the team on their toes. So there's obviously some homework to be done out there as well, Caitlin and the rest.
Thank you.
John, if I may, on
Yes.
behalf of the GSSA, I'd just like to thank Neil very much for putting these talks together. And to the other speakers, Caitlin, Alex, and Julian, for all the time and effort that goes into these talks. We totally understand the amount of work that goes into them. So thank you very much.
Thanks, Nolene. Certainly been a pleasure.
Thanks, everyone. See you next week.
Bye-bye.